Welcome, this is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium. This conference would not have been possible without our sponsors, PQ Shield, SSL.com, Entrust, Keyfactor, HID Global, and the organizational support of the Post-Quantum Cryptography Working Group of the PKI Consortium, and in particular, Entrust, Keyfactor, and Logius. Would you like to join the PKI Consortium? Go to pkic.org/join, or contact us if you would like to become a sponsor.
For our last presentation of the morning session, Jonathan Smith will be talking about FIPS 140-3 and PQC. With that, Jonathan, we're running a little behind, I think 5 or 6 minutes. So right after this session, we've got, sorry? 7 minutes. Sorry, I've been corrected. This is a pedantic crowd. So I think we've got a break after this session. So if we cut a few minutes into the break, I'm sure we'll be all okay with that. Certainly want to give Jonathan enough time to cover his talk and handle some Q&A.
Thank you. As you said, I'm Jonathan Smith. I'm a senior FIPS tester at DEKRA's FIPS 140-3 test lab. I've been doing FIPS testing for about 20 years, and so I wanted to give the test lab perspective on how this plugs into actually getting a FIPS validation. Let's see if I have any better luck with the slide. All right, so I want to start off with a quick summary of the FIPS 140-3 standard and sort of how algorithms in general work with it, then moving into the PQC algorithms, touch briefly on hybridization, and sort of move on to the algorithm-specific requirements, and then some wrap-up summary. Whoops, that's going backwards. Why does this keep going backwards? Just press the big middle button that looks like it's backwards. Okay. All right. So FIPS 140-3, it's a standards compliance program. It is the validation authority for it is the CMVP, the Cryptographic Module Validation Program, which is actually a joint program between the NIST in the US and the Canadian Center for Cybersecurity. It incorporates the international standard 19790, kind of extends that out. That standard relies on approved algorithms for its cryptographic security, and those are incorporated into annexes. In general, 19790 is set up where individual national bodies or validation authorities can plug in their own items into these annexes. And then, so the approved algorithms are split into two, depending on what type of algorithm it is. The key establishment ones are in the Annex D. All the rest of them are in Annex C. And then we have this 800-131 special publication, which is sort of CMVP specific, and it controls algorithm life cycles. So as we head into the 2030, 2035 retirement to the classical asymmetric algorithms, the way that gets fed back into FIPS 140-3 is through updates in this 800-133 standard, which provides more details about exactly how that transition is going to happen within FIPS. So the standard itself is much more than just the algorithms. So it's including module and key lifecycle. So all the ways the keys exist within the module, their creation, use, destruction, etc. It talks about roles and authentication, who gets to use the module, how they authenticate to it, what services it has, self-tests, physical security, and the specific requirements vary by level and module type in ways we're not going to get into today unless someone's got questions at the end. The requirements are split across a bunch of different documents. The 19790 itself, then there's what they call a derived test requirements document, which takes all the shall statements out of the main document and expands them with additional requirements on what vendors need to do to demonstrate they meet the requirement and what labs need to do to verify that. Then there's a special publication 800-140, where CMVP kind of modifies and extends that DTR slightly with some additional requirements. We have an implementation guidance document, which is very frequently updated and provides programmatic specific guidance on how to meet various requirements. That's where things get more detailed about specific algorithms or specific scenarios. And then we've got the annexes. I already talked about C and D, where the approved algorithms go, but we also have annexes for documentation, a public security policy document that's part of every FIPS validation, authentication, non-invasive attacks, which is kind of where things like side channel, well, where they would go, except that that annex is currently blank because they haven't figured out the objective test metrics for doing that yet. But that's the super high level of 140-3. So now I want to dive into the approved algorithms themselves, which is how PQC plots into this. So to actually use an algorithm to provide cryptographic security within 140-3, really 4 things need to happen. First, the algorithm needs to get standardized, usually by NIST, because they won't use something that's not a standard. Second, it needs to get added to the approved algorithm lists, because just because even NIST published an algorithm standard does not mean it's necessarily usable within 140-3 yet. It has to get added specifically to those annexes. Then we have to have some way of verifying that the algorithm is working correctly. And that's normally algorithm validation testing, which I'll talk a little bit more on in a second. Occasionally, and we'll see one example later, it's a guidance that allows vendors to affirm that it works correctly. And then finally, you basically need at least implementation guidance around the algorithm related to its how to do the self-testing, because the FIPS standard itself has very generic requirements about testing algorithms. You know, before their first operational use, perform usually some sort of known answer test. After you do a key generation for asymmetric, do some sort of pairwise consistency test. But the details are get put into the IG. And so until that's written, you can't really have an algorithm that's going to meet requirements because you don't quite know what they are. So, like I said, once they get approved, they get added to the relevant annex, and then we've got the algorithm validation. And so let's move on and talk about the algorithm validation process. So this is run entirely by NIST through what they call the ACVP, the Automated Cryptographic Module Validation Program. Chris Seeley does a lot of good work in there, creating the algorithms, and this is a black box testing, as I mentioned on this slide and on the next slide whenever it comes up. And so what that means is that for the algorithm validation, no one is examining the internals of the algorithm. It is, you send in your algorithm capabilities to the NIST servers. Based on those, they will generate a set of test vectors that they want the algorithm to process. Those will get run through the algorithm on its appropriate test environment to turn them into responses. Those responses get sent back to NIST server for checking and verification. And then all the details of this are on their GitHub, spelling out, in detail what you have to send in, what their vectors are going to look like. But the point is that this is a black box testing thing at this stage. And so until that test exists, you can't actually get an algorithm validation. And getting an algorithm validation is a necessary prerequisite to doing a FIPS 140-3 validation. So the actual NIST servers communicate to clients in JSON in the ways that are specified in that GitHub repository. They're broken into, as is very common for people, demo and production servers. The demo server, anyone can request credentials to access that. It can't be used to do algorithm validation. It's only used for basically test purposes. It's also where they will try out algorithms that are still in draft, or possibly even just some non-approved algorithms. So there's a broader range of things in that. And then once they're happy with the algorithm and it's approved, it will switch over to production testing. And that's what happened with the 3 recent PQC algorithms that were approved in August. They had been sitting on the demo server testing against the various draft standards for months before they went final. Then we have the production server, where access is restricted only to the accredited labs. It contains only actually approved algorithms, and it's used to actually issue the ACVP algorithm validation certificates. And then you would plug those certificate numbers in when you validate the module that uses that algorithm. The one thing I forgot to mention in that is that while the algorithm validation is black box testing, when the algorithm gets incorporated into a FIPS 140-3 module and that module is being tested, the test lab often has some additional requirements around the algorithms that they need to go in and verify through things like code review or design review. So by the time it gets into a FIPS module, it may be slightly more than algorithm black box testing, but it still relies heavily on that. So the post-quantum algorithms, nothing on this slide is a surprise, and all of it's been pretty much covered in greater detail in previous talks. But if we include the FIPS 208, we've got 7 approved algorithms from 4 different standards. Falcon is obviously still in development. We've got the forthcoming stuff that was talked about in the first presentation. So I'll just skip on. I want to cover quickly some of the timeline information around this. So what will be showing up is the status within them, and then the slide after that will be timing. So here we go. So in FIPS 208, your stateful hash-based stuff, it's got 4 algorithms in it. One of them is fully testable and approved. HSS is vendor affirmed with a particular IG, explaining how to do that. And then the XMSS and its variant are, there's no algorithm testing. So while they're approved, you can't actually use them in a 140-3 module at this time because they're missing one of those 4 key components. For the others that got approved in August, yep, they're fully approved, they're fully testable, you can use them, people have used them. And then Falcon is coming soon at some point. In terms of the timing, FIPS 208 was a really kind of slow adoption. The standard got published back in 2020, and it was about a year and a half before it got added to the 140-3 approved list. And then it was still about another year before algorithm testing for that came about. And even once that came out, it was several months before anyone actually got around to doing an algorithm validation on it. And the other in that standard don't have algorithm testing yet. But as we can see for the 3 new ones, MLChem, MLDSA, SLHDSA, the timeline was much more aggressive. They did a bunch more pre-work. And so everything that was needed to use them in a 140-3 module all dropped together in August. So August 13th, everything went live. The standard was published. It was added to the approved list. The algorithm testing went live on it. The guidance for it came out. And in fact, the first algorithm tests were completed and the first algorithm certificates issued within a day or 2. Now, we don't know quite how long it was until the first module using them was submitted, but it was probably within a few weeks of that, because there were certainly some people who were very eager to be the first to submit. But the review queue at CMVP is very long, and so we probably won't actually see the first modules containing those algorithms get validated until sometime this summer, maybe this fall. We'll have to see. I want to detour slightly into hybridization, just to basically reiterate what Andrew has said several times, which is that NIST is not taking a position on this. So PQCs are any other approved algorithm. Approved algorithms within 140-3 can be used for anything that the algorithm standard says they can be used for. And none of the algorithm standards say you have to hybridize. So it's certainly not mandatory. It is possible, though. For key establishment, because that's controlled by various standards, you do have to check the standards to make sure it's allowed, and it is. In fact, the special publication draft that came out last week, the, 800-227, has a section that even talks about this. It does explain in a bit more detail under the key generation standard, which I mentioned here, the 800-133, or even actually one of the key derivation standards, 856C, how you can combine the output of sort of classical key establishment with a KIM to generate a new hybrid key establishment. For signatures, the standard doesn't specify what you're allowed to sign or how many signatures you can apply to a piece of data or what sort of program logic you can have about making decisions based on those signatures. So it's just inherently possible to hybridize signatures. If you want to sign a piece of data with, I don't know, RSA and also MLDSA, it's fine. It completely meets the minimum requirements of FIPS. Now we can dig into a little bit of the algorithm-specific requirements for these. These are certainly not every shall statement in the requirements, but they're sort of the the unusual ones, the ones I wanted to highlight. So for your FIPS 208, your stateful hash-based signatures, the ones that everyone kind of likes to forget about or ignore, they have some odd requirements, and this was brought up earlier, which is that because of the extreme risk of the need to maintain that state and the compromise to the algorithm that would happen if you failed to properly maintain the state, it mandates that the private keys must reside within a module that has level 3 or 4 physical security requirements. It shall not be usable in the module's non-approved mode, whereas normally it's fine as long as the keys aren't shared. In this case, nope, you cannot use the algorithm in non-approved mode at all. You can have no export, import, backup, etc. of private keys. And that caused the discussion that was mentioned yesterday about between some of the industry folks and NIST and also NSA, because you might be doing signing with the firmware signing with these keys for a device family that could be in the field for 30 years, and your HSMs are only covered for 8 to 10 years. That's a bit of a problem if you can't migrate the keys to future HSMs. So that's an area that is currently under debate. Then, as we'll see in all of these, the implementation guidance 10.3a is the generic guidance on all self-tests for all algorithms, and it spells out the requirements for each of these as well as everything else. Because you can't have keys from anywhere else, if you have signature generation, you must support key generation. There must be a algorithm self-test for the key generation, which is a little unusual. That's not required for RSA or ECDSA. However, every time you generate a public, private, or asymmetric key pair within 140-3, you must have a pairwise consistency test on that newly generated key. And this spells out what that means for PQC, which is just confirming the same key identifier, as opposed to, for example, like RSA, where it's actually sign something and then verify something to make sure that that worked. So moving on to FIPS 203, we're going to see actually very similar requirements across all of the 3 new PQC algorithms. They all have minimum random bit generator security strength requirements depending on which parameter set you're using. MLChem also requires you to restrict access to the internal functions defined in the standard. And like all of them, it specifies you shall not implement it using floating point math. Because floating point is why Falcon is one reason Falcon's getting a little bit delayed. And then again, we've got the self-test requirements. It spells out what those algorithm self-tests need to be. It spells out that, again, key generation must have one. And it spells out that for decapsulation, you must cover both the implicit rejection and the non-rejection paths, so you need a little bit more extensive of a test there. And then you must need to have a pairwise consistency test when you do key generations, and that one's pretty normal, just encapsulate and then de-encapsulate. MLDSA, same sort of thing with the random bit generator. Strength requirements, same thing, don't use floating point math. Kind of similar requirements on the self-tests, although for signing, because they do have a new requirement, you have to cover all the applicable rejection sampling loop paths. They then, from the implementation guidance document, link out to this URL that I just pasted here that spells out in excruciating detail exactly what that means for a given setup. So you're going to have a fairly complicated self-test for this one. But verification self-test is easy. Key generation shall have a known test. And then the pairwise consistency is sort of your normal one, just sign and verify something. And then our last one, your SLH DSA, we've got the same random bit generator security strength requirements again, same no floating point math, similar self-tests, except the variation on this one is that this is defined with both SHA-2 and shake parameter sets, and if you support both types of parameter sets, then you must self-test at least one of each type of parameter set. Do a keygen self-test, and then the pairwise test, like the other hash-based one, is limited to just making sure the same key identifier exists in both. So it's a simpler, lighter weight pairwise test. And so that's really the special detailed requirements. Aside from that, they're just another approved algorithm, and you can use them like any other approved algorithm. At this point, just reminding people that 140-3 is the minimum requirements for the non-national security systems, for your sensitive but unclassified data, you are certainly free to go beyond these minimum requirements. And in fact, many of your customers may desire or require you to do so. So, you might have end customers who want hybrid crypto or want protocols that are PQC aware, because FIPS 140-3 itself does not mention protocols. It doesn't address them. It cares about the cryptographic algorithms or components that might live within them, but there's no statement or requirement in the standard about a protocol. But if you want the module version that you're getting validated to include some new PQC or hybrid aware, I don't know, TLS or whatever, you kind of have to wait until the protocol exists before you can implement it. Because when you're validating FIPS, you're validating a specific version of the product. And so if you make changes later, you're supposed to come back and get those changes revalidated. NSA's CNSA 2.0 requirements, if those do apply to you, because you are dealing with something with a national security system, yesterday covered it in much more detail, but one of those is software and firmware signing needs to be done with LMS, which means you would be required to have LMS support to meet NSA's requirements. But whereas FIPS 140-3 doesn't care, they'd be perfectly fine if you had a post-quantum software library that used HMAC as your integrity thing, or you had a post-quantum capable hardware module that used a non-cryptographic error detection code on its firmware. That would meet the minimum requirements of FIPS. That may not meet your customer's requirements. So just sort of telling you your own business of make sure that you're making what they want. I did mention the very long report queue, and that's kind of one of the big hurdles to getting PQC algorithms into FIPS modules, is that it takes so long just to get a FIPS module validated so that you can sell it into the government. The current delay between when the lab finishes its work and submits the report to CMVP and when they start looking at it is running at about a year. They are attempting to speed this up through various automation methods, so I did want to briefly touch on those, just make you aware that that's happening. Algorithm validation, like we already talked about, is already automated through the CMVP program, so that's why those algorithm certificates can get issued in a day. Entropy source validation, which we haven't otherwise discussed, is partially automated through their entropy source validation program. Module validation automation is something that's being examined by the National Cybersecurity Center of Excellence at NIST. There are some CMVP personnel involved in that, but that's not a CMVP proposal. However, they are expecting to have their initial proposal for that automation to present at the International Crypto Module Conference this year in April, and NIST, or sorry, CMVP has said that they will certainly look at that proposal and consider adopting some or all of it once they have a chance to see what it is. And then finally, the security policy document that I mentioned now has a somewhat automated review process in it, because they have moved to a structured format where all the required tables in it now must be provided to CMVP in a structured JSON format so that they can run some automated rules and consistency checking on it. And they've certainly reported, the reviewers have reported that significantly speeds up their sort of consistency review of the security policy and lets them focus on the sort of the policy issues and not double checking that everything is getting used correctly. So CMVP is hoping that's going to bring that 1 year down, but right now that 1 year delay is kind of one of the major hurdles in getting post-quantum into here. And so as a quick summary, labs are ready to do PQC 140-3 modules using those approved algorithms that have algorithm testing, because CMVP testing exists for that list of them. Certificates have already been issued for all of them. The first modules that actually contain those PQC algorithms are likely going to get validated this summer or fall. And we've got more algorithms coming, but that's going to take a while based on past performance. Like Falcon, from the time that first draft comes out until it's on the approved list and everything's ready to go, it's probably going to be about a year. And of course, it's going to be the same for your fourth round chems or the on-ramp things, except that they're going to get to that initial draft standard even later. So With that, questions?
Technically, we don't have time for questions, but we're going to make time.
Thank you. Couple of points I want to make. Maybe one is commentary and one is question. The commentary part is the ISO 19790. The FIPS, the CMVP program applies kind of literally. Whether it applies to the device under question or not, I've suffered through that. Last year, we had to provide updates to the implementation guidance through going into the CMVP user forum. I had to fight a lot and get some implementation guidance document to be updated to apply to SSD drives, right? For example, right? FIPS level 3, 140-3 level 2, we had some issues there. So that's a commentary part. The second is the ISO document. Is there any concerted effort, and maybe it's for the FIPS or it's for general community here, is there any concerted effort to upgrade the ISO document with these algorithms and make it applicable to, like a web server to an embedded device, to a drive, to a network controller? The requirements vary, and is there any concerted effort to tackle that in a more comprehensive manner?
You're definitely right that the standard as it's currently constructed is very much a one size fits all, which means it doesn't fit most modules particularly well, and you are required to meet all applicable things. And yeah, the CMUF, the user forum, has a request for guidance group that assists CMVP in trying to work out what that may mean for specific technologies. At this point, there's not an effort to turn the ISO standard into something that is more like profile based on the module types. In fact, I don't think they've issued the final release, but they're in the final draft candidate versions of the 2025 version update to that ISO standard, and it did not change the general outlines. It added some things, it made some tweaks, it added some stuff for attestation stuff, it added a secure containerization mechanism, but it's still very much the same one-size-fits-all design. It's not profilized. And so because ISO works on about 5-year review intervals, the next chance to do that, to push for that, would be in about 4 years when they start looking at the next round. And yeah.
Yes, my question is essentially the presentation was mostly about like level 3, level 4. So did everything you say also apply to level 1, level 2? Or the delay, like the 1-year delay, all of that, validation, automated validation? So is it all the same or a bit different?
Yeah, any full report, level 1, level 2, level 3, level 4, it sits in that same currently about 1-year queue. So it's just anytime you submit a full new report, it's a year before they look at it and even sort of determine what level it is. How long it takes them to review it can vary on security level, but just waiting for them to look at it does not. There's also, once you have a validation, there's various revalidation scenarios, and many of them do not sit in that queue, and they're much faster, but they're also limited on what you can do in them, and you've got to get through the queue to get your original certificate first.
I've got a quick question. So there's a lot of work, it sounds like, being done in the area of automation for the testing. Do you foresee that at all reducing that queue event at some point in time where it does become a little more manageable for some of the vendors out there looking for certifications?
That's certainly CVP's hope, because they're putting a lot of effort right now into automation at the short-term expense of time spent on reviews. And so they're certainly quite convinced that this is going to help. I hate to say, a little more skeptical, because we've been living with queues that have varied between like 6 months and a year for 15 or more years now, and they get a little bit better, and then something changes and it gets a little bit worse. We certainly had, the queue had gotten better before the transition to 140-3, but then all of the issues with switching to a new standard and learning that and changing their back-end systems to handle that just slowed everything back down. And we had a couple of algorithm transitions around key establishment that slowed things back down. We'll probably get more slowdowns as we phase out the classical symmetric algorithms, because people will be rushing to get the updated version, the next version of their thing validated with the post-quantum stuff, because they probably are going to wait to the last minute, because they always seem to. So I hope they've got to do something to get that queue down. It's ridiculous. I don't know how well the automation is going to work for it. It's supposed to be helping some with the security policy, but they need a massive speed up in review times to get rid of that queue.
Perfect. Thank you. Thank you, Jonathan.
Thank you.
How do you get to a quantum-safe state? That depends on the current state of your digital security infrastructure, as well as your level of visibility, control, and automation over those systems. Check your level of preparedness with the Entrust Post-Quantum Readiness Assessment. Whether you're already on the path to quantum safe or just beginning your journey, Entrust can equip you with the right knowledge and solutions. There are many paths to a quantum-safe future. Secure yours by taking the Entrust Post-Quantum Readiness Assessment today.